Hi mathematicians, welcome to this video today talking to you about prime factorization. Prime factorization is going to be an incredibly important concept in math that actually undergirds or underlies everything that we talk about when it comes to arithmetic. So we're going to talk about why this is important, what it's all about, and how we can actually use it in further concepts down the road. But first, let's figure out what some key vocabulary is before we get started. The first thing I want to talk to you about is what are natural numbers. If we look over here, if we look outside in nature, if you go outside into the woods, you can count leaves, you can count trees, you can count pebbles, you can count pine cones. It's that kind of season. And so the things that you can count are natural numbers. If you look out in nature, can you find 0 pine cones? Can you point to 0 pine cones? No, you can't count them. So that's why we don't count 0 as part of the natural numbers. Basically, the natural numbers are all of the whole numbers, 0, 1, 2, 3, 4, and so on and so forth, without 0. So the first natural number is 1, because you can count one of those things, okay? So the natural numbers are 1, 2, 3, and so on and so forth. The only whole number that is not a natural number is 0, yes. Okay, so let's talk about what a prime number is. You've probably heard this idea of prime and composite in the past, but let's talk about exactly what prime is, what a prime number is. A prime number is a natural number, so either 1, 2, 3, so on and so forth, greater than 1. That means we're not including 1. So what's the first natural number that we could consider? 2. Okay, this is really important to understand that prime numbers are natural numbers greater than 1. So 1 is not a prime number, okay? That has exactly 2 unique factors. Unique means completely different from each other. So 6 and 6 are not unique factors to each other because 6 is the same as 6. But 5 and 8 are unique factors because 5 is completely different from 8, okay? So that's what I mean when I say unique factors. So a natural number greater than 1 that has exactly 2 unique factors. Factors are numbers that can be multiplied by other whole numbers in order to make the number that you're trying to find. So sometimes factors are called divisors. These are numbers that can divide the number. That means you'll have a remainder of 0. So something times something will equal that number. There won't be anything left over, okay? So that's what I mean when I say factors, numbers that can divide that number. So 1 can always divide every number, okay? And itself. So say you have the number 2, for example, okay? 2 can be divided by 1. 2 divided by 1 is 2, with a remainder of 0. And then 2 can be divided by itself, which is 2. And 2 divided by 2 is 1. Now, just so you understand this idea of division, division is a way of rewriting multiplication. So if I'm saying 2 divided by 2, I'm asking what number times 2 equals 2? And what number times 2 equals 2? 1. And that's a whole number with nothing left over. 1 times 2 is 2, okay? So that's what I mean when I say is a factor of another number. I could rewrite this order right here because of the commutative property of multiplication. And I could say what number times 1 equals 2? That's 2, okay? So the only factors that divide 2 are 1 and itself. That's what makes it a prime number, okay? Prime number. So prime numbers have exactly 2 unique factors. Let's think of a number that's not a prime number. 4. We know 4 can be divided by 1 and itself, which is 4. But can it be divided by any other number? Can 2 divide that number? Yes. So it doesn't have exactly 2 unique factors. It has more than 2 unique factors. So we call those kind of numbers composite. Composite, okay? Composite numbers are natural numbers greater than 1 that have more than 2 unique factors, okay? So if every number that's prime is having exactly 2 unique factors, it has to explain what's happening with all numbers in general, okay? So there's this idea, there's this conclusion that we arrive at after we have taken all the facts of mathematics at play. And there's something called a theorem. A theorem is a conclusion that is made after all of the evidence has been gathered to prove that this is true. So we call this the Fundamental Theorem of Arithmetic, okay? Fundamental means at the base level, everything is built upon it, it's so important. Theorem is the conclusion of all of the things that are true about arithmetic. And that says this: every natural number greater than 1, okay? Every natural number greater than 1 can be written as the product of prime factors in exactly one way. Okay, so the product of prime factors in exactly one way. That means product is the result of multiplying numbers. So it's going to be something times something, potentially times something else. Of prime factors. Those numbers you're multiplying with can only be prime numbers. That's it. So exactly a number that can be divided by just itself and 1. And there's only one way to represent that number using prime factors. Now, you might have heard of when you multiply, you can put numbers in any order you want and you'll still get the same result or the same product. We call that the commutative property. You can change the order of numbers around a multiplication symbol without changing the result. Think of 2 times 3 is 6, and 3 times 2 is 6, okay? So that's what I mean when I say there's only one way to write it without thinking of the commutative property, okay? So that means there might be 3 2's that make up a number, and the only number on the planet that has a product of prime numbers with 3 2's. Let's see. Product is the result of multiplying, and we have 3 2's. We're going to have 2 times 2 is 4. 4 times 2 is 8. Okay? So 8's prime factorization is 2 times 2 times 2. All right? It's made of exactly 3 2's as factors. There's no other number on the planet that has exactly 3 2's as factors. Okay? And think of it this way, almost like every person has a unique fingerprint. Every fingerprint is unique to a different person, and so every number has its own prime factorization, okay? So you can think of this idea as numbers fingerprinting, way of distinguishing themselves. Okay, so let's talk about this idea of prime factorization. Okay, prime factorization, you're going to be asking to prime factor out a number. It's an expression, a number or numbers with operations, written as the product of, we know what product is the result of multiplying, the product of only prime numbers, only prime numbers. So to give you a sense of what prime numbers are, so we don't have to deal with having to think about them all the time, we're going to list out a set of prime numbers to begin with. So we have 2, 3, 5. Let me just go through this. Is there any way to make 6 without just using 1 and 6? 2 times 3, right? So 6 is not prime. 7 is prime because there are only 2 unique factors to make 7, 1 times 7. And then there's 11, 13, 17, 19, 23, 29, 31, 37, and we can keep on going on forever and ever, okay? There are an infinite number of primes. We're still trying to figure them out to this day. All right, so these are prime numbers, and we're going to try to express numbers as products of only prime numbers, okay? So here's our task. Find the prime factorization of the following numbers. So we're going to find the prime factorization of 24. That is, we're going to try to write 24 as the product of the result of multiplying numbers that are only prime numbers. One thing that we're going to do to help us out is make what we call factor trees, okay? And they're called factor trees because when you're starting to break down a number, it kind of looks like branches from a tree. So we call them factor trees. If a number is prime, we're going to circle the number, okay? If the number is composite, that means it has more than 2 unique factors, we're going to break it apart, okay? And then we'll be left with just prime numbers, and we'll write 24 as a product of just prime numbers, okay? So here goes. We ask ourselves, is 24 a prime or composite number? Is there just are there just 2 unique factors to make up 24, 1 and 24? Or can you think of any other number times another number that makes 24 without multiplying 1 and 24? You can think of 2, right? So we're going to break this number up. It's composite because it has more than 2 unique factors. We're going to, what numbers can multiply each other to make 24? We could take 2 times 12. And if you know that 2 is a factor, but you don't know what 12 is, off to the side over here, you can divide 24 by 2. And you can ask how many 2's are there in 2? 1. 1 times 2 is 2. 2 minus 2 is 0. Is this remainder less than what we're dividing by? Yes. So we pull down the next digit. How many 2's are in 4? 2 times 2 is 4. 4 minus 4 is 0. Any other digits to pull down? No, we're done. So it came out to be 12, okay? So 2 times 12 makes 24 because we have a remainder of 0, okay? Now we ask ourselves, is 2 a prime number? Why, yes it is, okay? So we're going to circle that. That number is going to be used in our factorization later. And now we ask, is 12 a prime number? Well, I know some divisibility rules for 12. Let's say any number that ends with a 0, 2, 4, 6, or 8, that is the last digit is 0, 2, 4, 6, or 8, is divisible by 2. That means 2 is a factor of that number. So I'm going to break this apart because I know it's composite. And I'm going to say 2 times what is 12? 2 times 6. Yes. Okay? So we know 2 is prime. Is 6 prime? I know 2 times 3 is 6, so it's not, because I thought of more than 2 unique factors, 1 and 6. So I break this apart, it's composite, and I say 2 times 3 makes 6. Is 2 a prime number? Yes. Is 3 a prime number? That is, it only has 3 and 1 that can divide it? Yes. Okay? So are there any other numbers I have to break down? No, that's it. So my prime factorization for 24 is 24 equals 2, it's a factorization, so we're going to multiply, times 2, times this 2, times that 3. So the prime factorization of 24 is 2 times 2 times 2 times 3. And just verify just to make sure that it actually equals 24. 2 times 2 is 4. 4 times 2 is 8. And 8 times 3 is 24. Now, some of you might have said, Mr. Almeida, I think I can make 24 without starting with 2 times 12. Am I going to get the exact same answer? Well, lucky for you, we have this thing called the Fundamental Theorem of Arithmetic, which says there's only one way to write the product of prime factors for every single number. So if I start with different factor pairs, I should be able to still break it down the same way, where I have 1, 2, 3 factors of 2 and 1 factor of 3. Let's break it down a different way. Let's take 24 and let's start with another number that can divide 24. Let's try 3, okay? 3 times what is 24? I know my multiplication facts, so 3 times 8 is 24. Now we ask, is 3 a prime number? Yes. Is 8 a prime number? No, I know 2 times 4 can be made, so 8 is composite. So I'm going to break 8 down into 2 times 4. Is 2 a prime number? Yes. Is 4 a prime number? No, because I know 2 times 2 makes 4, so I'm going to break that down into 2 times 2. Is 2 a prime number? Yes. And is 2 a prime number? Yes. So when we break it down, 24, we still end up with 1, 2, 3 factors of 2, and 1 factor of 3. The Fundamental Theorem of Arithmetic says, I don't care how you break down a number. There's only one way that it's going to break down, no matter how you start. So many people might have different factor trees or different ways of thinking about it, but in the end, you're going to end up with 3 factors of 2 and 1 factor of 3. 3 factors of 2 and 1 factor of 3. So that's 24's unique prime factorization. 3 factors of 2 and 1 factor of 3. Okay? So that's the prime factorization for 24. All right? The product of just prime numbers. You can't have a composite number in there, otherwise it's not the prime factorization. Okay? Let's move on to 30. Okay? Let's prime factor out 30. So we ask ourselves, is 30 a prime or composite number? I'm looking at this and I know that 10 is a factor of this because I know any number that has a last digit of 0 in it is a multiple of 10. So therefore, this number is divisible by 10. 10 is a factor that can make 30. What number times 10 can make 30? 3. So I'm going to break this number apart into 3 times 10. Okay? Okay? Is 3 a prime number? Yes. It can only be, it only has 2 unique factors, 1 in itself, 3. Is 10 a prime number? No. I know that 2 times 5 makes 10, so therefore it is not, it is composite. So I break it down into its other components, which is 2 and 5. Is 2 prime? Yes. Is 5 prime? Yes. So what is 30's prime factorization? 30 is equal to 1 factor of 2, there aren't any other 2's here, times 1 factor of 3, there aren't any other 3's that I've circled, times 1 factor of 5. So 30's prime factorization is 2 times 3 times 5. And before you settle on what your prime factorization is, go through the multiplication to verify that that's what it actually equals. 2 times 3 is 6. 6 times 5 is 30. So this does equal 30. Now I just have to do one more thing. Are all of my factors prime numbers? That's prime, 3 is prime, 5 is prime. So yes, this is the prime factorization of 30. And we'll do one more, okay? We have 42. We ask ourselves, is 42 a prime number? No, it's composite. So we're going to break it down into what? 6 times 7, that makes 42, okay? So I broke it down into 6 times 7. Is 6 a prime number? No, I know that 6 is made of 2 times 3, so I'm going to break that down. Is 2 a prime number? Yes. Is 3 a prime number? Yes. Is 7 a prime number? Yes, it is, okay? And that's it. I've broken this down to its prime factorization. So 42 is equal to 2 times 3 times 7. And just verify before you're done to make sure this is the prime factorization. 2 times 3 is 6. 6 times 7 is 42. So that does equal 42. And just verify, do you have all prime factors? Is 2 prime? Yes. Is 3 prime? Yes. Is 7 prime? Yes. This is the prime factorization of 42. And that is how you find the prime factorization of given numbers. Now, there is a shorter way to write out 2 times 2 times 2 times 3. It's called exponential notation, where if you see repeated factors written down, you can abbreviate it by keeping track of what that factor is. So what factor do you see repeatedly written? You see a 2, so we call that the base. We see a base of 2. How many times is 2 written as a factor? Once, twice, 3 times. So we would say this is 2 to the 3rd power. This power tells you how many times you're going to write 2 as a factor. That means number times number, okay? How many times are you going to write 2 as a factor? 3 times. So you would think of it as blank times blank times blank. Those are 3 blanks. And then what's going to go in each blank? The base of 2, okay? So I have 2 to the third power. This is just a shorter way of writing it out. It's called exponential notation. It's a shorter way of writing out repeated multiplication. And then I'm going to multiply it by 1 factor of 3. So you could say 3 to the, how many times are you writing 3? Once. You could write 3 to the first power, but most people just write times 3, where we assume that it is to the first power, okay? So a shorter way of writing it out would be 2 to the third power times 3, okay? And that says 2 times 2 times 2, that's 2 to the third power, times 3, all right? And then you only see 1 factor of 2 here, 1 factor of 3, and 1 factor of 5. So this is the shortest way to write out this factorization. And you see 1 factor of 2, 1 factor of 3, 1 factor of 7. There aren't any factors that repeat, so therefore this is also the shortest way of writing out this factorization. I hope that throughout this video you've learned how to prime factor out numbers. Just as a recap, prime numbers are numbers that only have exactly 2 unique factors, 1 and itself. And the Fundamental Theorem of Arithmetic says that every single number can be broken down into prime factors in exactly how many ways? In exactly 1 way. And that way, it doesn't matter about the order of the factors, you're going to have a unique way to identify that number when you write it out as the product of just prime numbers. And that's what prime factorization is all about. I hope you enjoyed this video, and I hope that you use this knowledge to help you as you learn about other concepts such as the least common multiple and the greatest common factor. And I wish you all the best in your journey throughout mathematics. Take care, mathematicians.